Hi everybody, my name is Przemysław Koprowski and this is the first lecture of a mini course on computational mathematics. I say mini course because this course consists of only 15 hours of lectures. All the materials that I will be talking about, all the stuff that will be covered in this course can be found in the lecture notes which are available online at www.pkoprowski.eu/LCM. LCM stands for Lecture of Computational Mathematics. Computational mathematics is a very broad area of mathematics, and so we must, having only 15 hours, we must concentrate on a particular part of this area. So the main aim of this course, the main goal of this course is to show you methods for solving system of nonlinear equations. Usually at the very beginning of mathematical studies you learn the methods to solve system of linear equation like Gauss elimination, for example. However, nonlinear equations are far harder to solve. So during this course we will develop methods that will allow you to solve such systems. Moreover, these methods will be not just numerical methods. We will concentrate here mostly on symbolic methods, so the ways to find exact solutions of such systems. We begin with a simple example which will somehow motivate us and to some extent will advertise what will happen during this semester, what kind of problems you will be able to tackle at the end of this course. Everybody knows how industrial robots look like. This is a number of rigid parts connected by some joints. The joints can rotate in a certain range of angles. They have a certain level of freedom, and they are used to work in high industry to construct cars, ships or whatever. From mathematical point of view, we can think of such an industrial robot as a sequence of points such that two successive points are in constant distance from each other. So A is in constant distance from B, B is in constant distance from C, and C is from constant distance to D. And at each of these points, these points represent the joints of this industrial robot. There is some angle, or in three-dimensional case there will be a triple of angles with respect to each of the canonical directions. Here, for simplicity, to make the picture easier to read and easier to draw and easier to grasp, I draw it in just two-dimensional case, so there is just a single angle at each joint, and there is some target when the effector, this last point D, should be positioned. Of course, in one direction the problem is really trivial. If we know the angles alpha, beta, gamma, and we know the lengths of all these three line segments A, B, B, C and C, D, this is just a basic trigonometry to compute the position and the orientation of point D. This is really trivial. Strongly non-trivial is the inverse problem. We know where the point D should be positioned, we know the target, we know the orientation of this robot at the target, so we know from which direction the point D should approach the target, and knowing these two things we need to compute corresponding alpha, beta and gamma. I strongly encourage you to try to do it after the lecture, try to do it yourself on a piece of paper to see how difficult this problem really is. you will see that you encounter a system of highly nonlinear equations. You will have a system of trigonometrical equation to solve, which is in general quite hard. Throughout this course, we will develop methods to deal with systems of nonlinear equations, more specifically with systems of polynomial equations. So this system can be this problem can be translated into a system of polynomial equations, and the tools that we will develop during this course, so-called Grobner bases, allows us to explicitly solve this problem. So if we encode this problem in form of a system of polynomial equation, or more formally in a form of an ideal in the polynomial ring, then when we apply the Grobner basis to it, we will get a solution, explicit solution, a function that takes as its parameters, it takes the position of D and the expected solved orientation, and it returns the angles alpha, beta, gamma in this case, or in more general, it will work in any number of dimensions, so it can work in a three-dimensional case when we will have not just three angles, but three triples of angles. Let me show it that it really works. Let me show you an example from the last worksheet that we will do in this semester. What you see now on screen is a worksheet in Sage. Sage is a system for doing computational mathematics that you will use on labs, and here I can enter the position, expected position of a vector. This blue circle represents the vector. If I change the position to, let's say, this position, you see that this system actually computes and finds the angles and positions this robotic arm in the position I want. I also can change the angle, the orientation of this last segment, so let's say that it is to be 3 over 8 pi, or we can change in another direction like this, and whatever I enter here, it always computes the correct position, or says that the position is unreachable for this robot. We can even order it, we can even enter as an argument not just a position but the whole curve, which is really what you need in applications. If you think of the application of the industrial robot, it can be used, for example, to paint a car. So we want this effector, which this last part of a robot, which is a kind of a nozzle. We want this nozzle to move on the certain trajectory and be directed toward the car, so that the paint is applied to the car, and we can actually achieve that with this system that we will develop during this semester. As you can see here, if we have a certain trajectory where this effector is expected to move, this still works. So this is really effective method. This is working actual method to solving this kind of problems. Of course, what we will do during this semester is not just solving a problem in robotics or in kinematics. We will develop a general framework that can deal with any system of polynomial equations. So any problem that can be translated into a system of polynomial equation, like this robotic problem, can be solved or will be possible to be solved using the methods that we will develop throughout this course. Nevertheless, before we reach the level of Grobner bases and things like that, we need to first deal with far more basic concepts. This course has virtually no prerequisites. We start from absolute beginning. All you need to know to attend this course is to know what polynomials and integers are, basically nothing else. Let me shortly call what are the most basic building blocks of in computational mathematics, or more precisely in symbolic computation, because this first lecture, today's lecture, deals mostly with fundamentals. Here on this today we will develop a number of very elementary algorithms that deals with basic objects, and these algorithms will be building blocks for what we do next. So we start from beginning, we start from ground zero, from basic arithmetic, addition, subtraction, multiplication, and things like that, and slowly throughout the course we will develop more and more advanced object, more and more advanced operations, and all of course these more advanced operation will depend on these basic blocks. So our first task is today's task is to talk about what we talk today are just the basics. So let me start with, as I said, basic building blocks of everything that we will do. These are integers and polynomials. They are very similar to each other because integers are nothing else but finite sequences of digits, where a digit is just something depends on the base that we take. If for us human beings the most natural base is base 10, because we have just 10 fingers at both hands, so the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. For computers more natural are the binary systems, so the digits are 0 and 1. For computer algebra systems, so not a hardware level but on the higher level, probably most natural are the powers of 2, so a digit can be a byte, so any number between 0 and 255. Anyway, integer of arbitrary size is just a finite sequence of such digits. Likewise, polynomials. Polynomials are finite sequences of coefficients. So internally, polynomial inside a computer, so let's say we have a polynomial f equals f0 plus f1 x plus and so on plus fm x to the nth power. Internally, from the point of view of computational methods, from the point of view of computer algorithms, it is stored as a sequence of its digits f0, f1 and so on up to fm. Likewise, integer, if we have some integer n, when we can think of this integer as a sum of powers of digits times the times a certain base, so we have a fixed base, beta is base and it's fixed. So we can think of the integer as either plus or minus some n0 plus n1 beta plus n2 beta square plus and so on nk beta to the kth power. So again internally, from point of view of symbolic computation, computer algebra, n is represented as a sign, this is plus or minus, and a sequence of coefficients. We can write it, usually we start with the leading coefficient, leading digit, and we end here with base beta. So for example, if n is minus 123,047, then this is nothing else but just a representation of a decimal representation of a number minus 1 times 10 to the minus 1 times 10 to the 5th power plus 2 to the times 10 to the 4th power plus 3 times 10 to the 3rd power plus 0 times 10 plus 4 times 10 plus 7. So as you see, this is very similar to polynomials. So it does not come with a big surprise that algorithms for integers and algorithms for polynomials are very similar to each other. In fact, algorithms for polynomials are teeny tiny, simpler and easier because we do not have a carry to take care about. As I said, we start from ground zero. We start from basic arithmetic, from addition and subtraction. So I hope you all know how to add and subtract polynomials. So if we have two polynomials f and g, one of degree m, one of degree n, then its sum or equivalently difference because it's all the same. So its sum is a new polynomial of some degree k, such that each coefficient of this result is respectively a sum or a difference of the corresponding coefficients of fi and g of f and g. Of course, if the degrees of these two polynomials do not agree, so if one of the degrees is less than the other, then we just treat the missing coefficients as to be equal 0 by definition. So we can express this in a compact formula that hi is fi plus gi if I does not exceed the minimum of the 2 degrees, and once we reach the minimum, then we just rewrite the tail of this polynomial. So this clearly defines the addition and subtraction of polynomials. For this is the first algorithm that we deal with, so I will rewrite it once again in an explicit form. So the algorithm works like this. As an input we are given two polynomials f and g. Both are represented as sequences of coefficients, and as an output is their sum or respectively difference h. So we take the minimum and maximum of the degrees of the two polynomials, and then we have a for loop, so definite loop starting from 0 up to the minimum, and we either add or subtract the corresponding coefficients of the two polynomials, and once we reach the minimum, then up to between minimum and maximum we just rewrite the tail of one of the polynomials. If we subtract the polynomials and we are rewriting the g, then we need to change sign. That's all. So the formula for adding and subtracting polynomials can be directly converted into such a such an algorithm. Observe one more thing, that if the degrees of the two polynomials differ, then of course the degree of the result is the maximum of the two. If they are the same, then the leading coefficient can cancel, the leading terms of two polynomials can cancel each other, so it is possible that the degree will be smaller than the maximum. Addition of integers, or more exactly addition of positive integers, so natural numbers, is almost the same. It's almost the same except one thing. If we add two digits, then the result can be no longer a single digit. For example, if we add the base 10 in decimal system 8 plus 3, then the result is 11. It's not a single digit. This consists of a carry 1 and a resulting digit 1 again. So we need to take care of this carry, and so in order to compute the sum of two integers represented again as sequences of digits at a given base beta, we do almost the same thing as we do for polynomials, but we have additional auxiliary variable c that is a carry. So we add the two digits to each other, but we compute its remainder modulo beta, and this remainder is the new digit of a result. But it is possible that we have a carry, so like 8 plus 3 we have a carry 1. So this is nothing else but the standard way of adding integers that you learned at primary school. We just school way of adding integers, and it directly translates into an algorithm. So finally, what we do is, in a loop, we add digit to digit plus the carry that we have. We compute the remainder. If the remainder modulo of the base, the remainder is the next digit, and if we have a carry, then we just pass it to the next two digits to add. And if we used all the digits of the input, but we still have a carry, then this last digit that we add one more digit that is equal the carry, and the carry in this case is always 1. There is nothing else possible when we add numbers to each other. This solves the problem for adding positive integers. Subtraction of positive integers if a is greater than b is very similar, is really almost the same. So again we have two sequences of digits, and we compute the differences step by step. First we subtract one from the other. If the least digits are, if the least digit of a is greater or equal to the least digit of b, we just subtract it for each other. Otherwise we add beta to it and have a carry 1, and then again digit by digit we perform the same action. We subtract one from each other, and we update the carry step by step. So this is nothing different. This does not differ from what you learned at primary school. I just write it down explicitly in form of an algorithm, so you see that this method of adding and subtracting numbers can be directly translated into algorithm, and can be implemented in computer algebra system. Finally, addition and subtraction of arbitrary integers can be done in form of addition and subtraction of positive integers, just depending on the signs of both integers. So if both integers have the same sign, then addition is just the addition of the absolute values, so we ignore the sign, we add the two natural numbers and we rewrite the sign. if the signs differs, then we can always select the number which is greater, subtract the number with a smaller absolute value from the number with a greater absolute value, and use the sign of A. Once we have addition, we can define subtraction by just adding an opposite. So the next step after addition and subtraction is of course multiplication. And again, the simplest multiplication algorithm you all know from school. This is a so-called long multiplication or school multiplication of polynomials. So if we have two polynomials and we just multiply, and then we multiply it each term of one polynomial's time each term of the other polynomials, and we group together the terms that have the same exponent of x, then we arrive at the following formula that you see here. So the product of two polynomials is a polynomial h of this, which looks like this. Of course, I believe that you all know it from school, so I will not prove this formula because it's obvious. You all know how to multiply polynomials. But let me do one example just to show the complexity of this multiplication, because it will in a moment you will see that there is a better way of multiplying polynomial. While addition and subtraction we have no way to improve. They both were linear in terms of number of coefficients and nothing can be improved there. But for polynomials actually there is a room for improvement. So as I said, let me do a simple example. Let's take the following two polynomials and I will compute the products using long multiplication, and I will do it in a very explicit way so we can easily see how many products of a coefficient we really need here. So I will write everything explicitly. So f times g equals 1 plus 2x plus 3x squared plus 4x cubed times 3 plus x plus 4x squared plus 2x cubed. It equals, and now we just, in order to get the constant term, we need to multiply the constant terms by other. So 1 times 3 plus, in order to get the linear term, we multiply 2 times 3 plus 1 times 1 x. Now the square term, so it's 3 times 3 plus 2 times 1 plus 4 times 1 x squared plus, now the cube part, it will be like this: 4 times 3 plus 3 times 1 plus 2 times 4 plus 2 times 4 and 1 times 2. It's 1 times 2 x cubed plus, now we take x to the 4th power, so it's 2 times 2 plus 3 times 4 plus 4 times 1. 4 times 1 x to the 4th power, now x to the 5th power, so 3 times 2 plus 4 times 4 x to the 5th power, and the only way to compute x to the 6th power is to multiply the leading terms of both polynomials, so it's 4 times 2 x to the 6th power. So if we compute it, we have 3 plus, now we have 7x plus, here you have 15x squared plus, Now we'll have 25x cubed plus, here we have 20x to the fourth power plus, now it's 22x to the fifth power plus 8x to the sixth power. So let me count the number of products of coefficients we needed to compute in order to get the product of the two polynomials. We had exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Total of 16 products of coefficients. So the long multiplication, the standard way of multiplying polynomial that we learned at school, needs for just these two low degree polynomials, of the polynomials of degree 3, it needed 16 products of the coefficients of the polynomials involved. Just analyzing the formula, we see that the multiplication of two polynomials using long multiplication needs around d square products of coefficients, where the d is maximum of the degrees of the two polynomials. So what we can ask whether there is an algorithm that is actually faster, if it's possible to use lower number of multiplications of coefficients. And in fact, such an algorithm exists. It was quite surprising. Of course, first it was not first considered for polynomials. It was originally considered for integers, and it was a problem that people believed about 50 years ago, that okay, that product of two integers needs around d square number of products of digits, where the d is the number of digits, is maximum number of digits. So it was quite surprising that when Karatsuba, it was at that time he was just a student, came out with a completely new algorithm for multiplying. His algorithm was originally developed for integers. I will present it here for polynomials, because for this course the polynomials are the more interesting objects. And Karatsuba invented an algorithm that deals with products of, well, as I said, integers or polynomials in a lower number of that needs a lower number of products of coefficients or digits. The idea of this of Karatsuba algorithm is to recursively split a polynomial in halves, into a lower and upper halves. Let me show it on explicit. Let me show it how it works. So suppose we have this polynomial f, and we write it as a lower part plus the upper part times x to the some power d. And we do the same with the polynomial g. It's just a lower part plus the upper part times x to the d power. If I multiply it in a naive way, so if I multiply it directly, so it will be fl plus fu x to the d power times gl plus gu x to the d power. Then I will arrive at the following formula. It's fl gl plus fl gu plus fu gl x to the power. Here of course FL, GL, FU, GU are polynomials, not just coefficients, are polynomials in half of the length of the original polynomials. And then finally we have FU, GU, x to the d. Here we have four multiplication of polynomial of half a length, 1, 2, 3, 4. So we don't have any we have nothing. It is no way better than originally. We don't have any gain here. However, the very smart idea of Karatsuba was to write it in a different way. So let's forget about this formula. Let's forget about the original formula. Karatsuba proposed to multiply the polynomials in a different way. So let's rearrange the terms in the formula. So what do we do? Okay, the lower parts are multiplied in the same way as here. We don't change anything. The upper parts, FU, GU, will also not change, but the part in the parentheses will be rewritten. We write it in this way. We add lower and upper part together, FL, FE plus FU, and we multiply it by GL plus GU. What we get is we have FL plus GU. Okay, we should have FL plus GU, and we'll get it. Okay, let me show. If I take here FL and here GU, then I will get this part. If I take here FU and here GL, I will get this part. But I will get two extraneous parts that I don't need. I will get FL times GL here, that I don't need, so I must subtract it. So I subtract FL times GL. I will also get FU times GU, which I don't need either. So I subtract it too. So FU, GU. And now this is the same. And now I rewrite the last formula, FU, GU, x to d. Okay, so it's clear that the result is exactly the same. We must wonder if this is any better than it was before. If we may think, okay, this formula is even worse, it's more complicated, it's longer, and so on. But if we look carefully at it, if we analyze it carefully, that we'll see that we have actually only 3 multiplications here. We have one multiplication here, we have the second multiplication here. Okay, I will denote it by double line, and we have the third multiplication here. And the two remaining products are already computed, because here we have again FLGL. So this is the part that we have already computed. We don't need to compute it twice. It's enough to compute it once. Likewise here we have FUGU, which is the same as the last term. So we don't need to compute it twice. It's sufficient to compute it once. So instead of 4 multiplications as in the previous formula, here we have 4 products. Here we have only 3 products. So we actually we get rid of one product of polynomials of half the length. And we could do it recursively, and this algorithm works recursively, so the polynomials are split in half as long as we don't get to the level, to the linear terms, or to the constant polynomials. So the formula that we just derived is the following one. This is Karatsuba formula for multiplying polynomials. So the As I said, the Karatsuba algorithm is recursive, so explicitly we are going to work like this. We take two polynomials, we compute the point where we will, the degree at which we will split these two. So this is roughly half of the length of the two polynomials. And we compute half of the maximum length of the polynomials. And we compute the product as follows. We have two special cases. The special case is if any of the two polynomials is 0, then we don't need to compute anything. We just know that the result is 0. There is no point in multiplying anything by 0. The 0 times anything is 0. So we stop here. We return 0 and we stop. There is a stopping condition, there is a terminal condition when both polynomials are constant. So there is no way to split it any further. They just consist of a single coefficient. If both polynomials consist of a single coefficient, we just multiply these two coefficients, f0 times g0, and this constant is a resulting polynomial. In any other case, if the two polynomials have higher degrees than if they are not constant, then we split both polynomials roughly at half. So we split it at the degree d that we computed at the very beginning, and we call this algorithm, we apply this algorithm recursively to compute the three products, fl times gl, fu times gu, and the product of the sums of lower and upper parts. Then we have these three products computed, we recombine them using the formula that we just derived, and we just compute them together using the Karatsuba formula. So here instead of this part we just use the Karatsuba formula, so we just take this thing, subtract this thing, and subtract this thing. So this is exactly the Karatsuba algorithm. So now let's see if it is in fact any more efficient, any faster than the standard long multiplication. Indeed it is. I will compute the same product of the two polynomials, but now I will use Karatsuba algorithm. So we again have these two polynomials. I will compute the product using Karatsuba algorithm, but I will draw it as a scheme, as a diagram, because this way it's easier to grasp it. So I will start here. So we have 1 plus 2x plus 3x squared plus 4x cubed times 3 plus x plus 4x squared plus 2x cubed. We need to split both polynomials at half, so here and here, and we need to separately compute the product of the upper, lower parts and their sums. So the upper parts will be 3 plus 4x times 4 plus 2x. This is the upper part. Now the sums of these two is 1 plus 3, 4, plus 2 plus 4, 6x, times 3 plus 4, 7, plus 1 plus 2, 3x. And now the lower parts, it will be 1 plus 2x times 3 plus x. Again, none of these polynomials are not constant. None of them is 0. So we, using the Karatsuba algorithm, we need to split them at half, all of them. So we are splitting them here at half. And again we have the same thing, the lower part, the upper part, and the sum. So the lower part is 3 times 4, the upper part here is 4 times 2, and the sum is 3 plus 4 is 7, times 4 plus 2 is 6. Here the same. So we have 4 times 7, we have 6 times 3, and we have 10 times 10, and the same here is 1 times 3, it's 2 times 1, and it's 3 times 4. Okay, we can now easily compute all these products here. It's 8, it's 42 here, 12, 18, 100, 28, 2, 12, and 3. And now we need to recombine them using the Karatsuba formula to compute the products of polynomials we started with. So it will be like this. It is 12 plus, now we have 42 minus 12 minus 8 times x plus 8x squared. Here the same is 28 plus 100 minus 18 minus 28 x plus 18x squared, and here the same is 3 plus 12 minus 2 minus 3 x plus 2x squared, and of course we can easily compute this. Is 22 here, here we have 54, and we have here 7. So now we recombine these 3 things together to get the resulting polynomial. So it is 3 plus 7x plus 2x squared plus, now the difference between the middle part and the upper and lower parts, so it's 28 plus 54 plus 50 or x plus 18x squared minus 3 plus 7x plus 2x squared minus 12 plus 22x plus 8x squared, and this is time x squared, and finally we have 12 plus 22x plus 8x squared times x to the 4th power. All in all, this thing equals 3 plus 7x. Okay, I will compute the term in parentheses here. So it's 28 minus 12 is 16. 16 minus 3 is 13. 54 minus 22 is 32. 32 minus 7 is 25. Plus 25x. 18 minus 8 minus 2 is 8. So now we have 2x squared plus 13x squared, so it's 15x squared plus 25x cubed, and now we have it should be plus 8, 8 plus 12 is 20. 20x to the fourth power plus 22x to the fifth power plus 8 times x to the sixth power. We see that the result is the same as before. Of course, it must have been the same as before because this is just the product of the two polynomials. It is the same. It may look on your once when you see it for the first time, you may have an impression that this is more complicated, more time-consuming than that computing it using just the school method, long multiplication. It is so because, first of all, you see it for the first time. You are used to long multiplication for years, and you see this new method for the first time. Secondly, I wrote it in a very long, very explicit way, so you see all the steps. I didn't do any step by heart. I didn't compute anything outside the paper. I wrote absolutely everything here, so it looks worse, it looks longer, but let count the number of products of coefficient. Let's check objectively if we have really more things to do here, more computations to do here, or less than in a standard long multiplication. Observe that there was only one place when we had to compute the products of coefficients. This was the only place here. This is the only place when we computed the products of coefficients. There are the only products here. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have a total of 9 products here. Comparing to 16 products in a long multiplication, this thing is really faster. We have, even for so low degree polynomials, these are low degree polynomials, degree of both polynomials are 3. Even for so low degree polynomials, this method used lower number of multiplications. So now let us find the asymptotic complexity of a Karatsuba algorithm. Let D be the maximum of the degrees of the two polynomials involved. So the number of recursions the number of times we need to split these polynomials into half is nothing else but just the log at base 2 of D. And at each recursion, each time we call this algorithm recursively, we have 3 products of the polynomials of the half length. Products of half length. So all in all, the complexity of our algorithm this is big O of 3 to power log 2 of D. But now what we can do is 2 to the power log 2 of D. We can write it as 2 to the log 2 of 3 to the log 2 of D. And now, using the standard properties of the logarithm, this is nothing else but 2 to the log 2 of D times log 2 of 3, and this is nothing else but 2 to the log 2 of d to the log 2 of 3, and this is d to the log 2 of 3. So this is actually the complexity of the algorithm. So the complexity of the Karatsuba algorithm is O of d to log 2 of 3. And log 2 of 3 is roughly 1.6, so this is the complexity of a Karatsuba algorithm. So as you see, this algorithm is asymptotically faster than long multiplication. Of course, like in many other places, there are also the constant factors that need to be taken into account. So for low degree polynomials, really the long multiplication will beat because it generally has a lower constant terms. But when the degree of the polynomials arise, when the degrees are bigger and bigger, then the Karatsuba will eventually always beat the long multiplication. As we have seen, even for very low degree polynomials, for polynomials of degree 3, the actual number of coefficients was lower in the Karatsuba algorithm. So even with these additional steps that we need to perform, like splitting the polynomials and so on, if the most time consuming operation is multiplication of coefficients, and it is usually so, then the Karatsuba algorithm will be faster. Actually, the Karatsuba algorithm is not the fastest algorithm known. On the next lecture, we will learn an even faster algorithm. We will learn a completely different method of multiplying polynomials that beats even Karatsuba. But now we are at this subject of the fundamental algorithms, and as you see, we have the long multiplication, which has quadratic complexity, and we have a better algorithm due to Karatsuba, which is complexity of the d to the power roughly 1.6. And now when we have addition, subtraction and multiplication of polynomials, the next is naturally expected thing is to cover division, but before we go to division, we will first tackle two simple algorithms, two simple operations. First of them is computation of a derivative of a polynomial. That's the first place. That's the first place where polynomials and integers differ. So far, addition, subtraction, multiplication was the same or nearly the same for both polynomials and integers. Derivative is the first real difference. We have a well-defined and easy to compute derivative of polynomials. We can differentiate polynomials, but there is problem. Actually, this operation does not have a real counterpart for integers. There is such a thing as arithmetic derivative, but it's neither easy to compute nor so useful as a derivative. The fact that the polynomials have a well-defined and easy to compute derivative has far-reaching consequences. In fact, we'll see in a couple of weeks that due to the fact that polynomials, that we can differentiate polynomials, we can compute the derivative of polynomials. One of the consequences is that it's relatively easy to compute, to factor polynomials into square free parts. In fact, it's quite easy to completely factor polynomials as well. We will not talk about full factorization of polynomials, but square free factorization of polynomials to the square free parts will be covered in one of the lectures of this course, and we will see that due to the fact that we have a derivative, it is easy to do it, while it's very hard to do it for integers. So this is a real difference. This is a big deal. So as far as the polynomial derivative is concerned, it is a very easy operation. We all very know well that derivative is additive, it's linear, and we know the formula that the derivative of x to the nth power is n times x to the n minus 1 power a times f derivative, where a is constant, is nothing else but a times f derivative, and f plus g derivative is f derivative plus g derivative. These three known properties of the derivative give rise to the algorithm that we see here. So we take this polynomial, we use the last property of additiveness of the derivative, and so we treat each of the terms separately. For each term we apply the second property, so the derivative of fi x to the f power is I plus 1 is I times fi to the x to I minus 1 power. So all in all, if we have this polynomial, we compute that. So if f is f0 plus f1x plus fm x to the nth power, which is represented as a sequence of coefficients f0, f1 up to fm, then its derivative f1 plus 2 f2x plus 3f3 x squared, and so on, m fm x to m minus 1 power, which is represented as f1 to f2 3f3 and so on m fm. So as you see, the position of each coefficient is shifted by 1. This corresponds to this change of indexation. So on the mu ith position is the coefficient which was previously on I plus 1 position. That's why here we have I plus 1, and this and each coefficient is multiplied by its index, which is the exponent of x in the original polynomial f. So all in all, this is the algorithm that computes the derivative of a polynomial. Now the second algorithm that we will want to tackle is the evaluation of a polynomial at a given point. So we have a polynomial f and we have some point a, and if we evaluate f at a, so we compute f of a in a naive way, then we will need the following number of operations. So a naive approach to evaluating f of a would be something like this. This is f0 plus f1 times a plus f2 times a plus f3 times a times a times a, and so on. Finally we will have fm times a times a and so on times a. So here we have 0 multiplications, here we have 1 multiplication, here we have 2 multiplications, 3 multiplication, and so on. Finally here we have m multiplications. All in all, the number of multiplications of coefficients is 0 plus 1 plus 2 plus and so on plus m. So as we see here, it's m times m plus 1 multiplication. So the complexity of evaluating polynomial in such a naive way is as it's obviously quadratic. But it is easy to observe that this is really a naive way, because we separately compute a square, a cube, and so on and so on every time we do all the multiplications. But it's obvious that if we already computed a square and we want to compute a cube, we don't need to multiply a 3 times by itself. It's enough to multiply a square by a again. Now when we have a cube and we want to compute for the 4th power of a, we don't need to multiply a 4 times. It suffices to multiply the a cube that we already computed by a once. So it is quite easy to improve this algorithm and reduce its complexity. Indeed, so what we do now is so-called corner scheme. Corner scheme looks like this. We rearrange the terms. We write the algorithm other way. So if we have f, we take the constant term f0, and now all the other terms are divisible by x. So we write x times and the other polynomial. Now this other polynomial has again a constant term, which is f1, which we write separately, and all the remaining terms are divisible by x. So we again take x outside and we repeat this process. So if we rearrange the terms this way, this is, as I said, called corner scheme, then the evaluation of polynomials is the evaluation of a polynomial is as follows. We start with the result. We initialize the result to be the leading coefficient fm, and now we step down with the index from the highest to the lowest. Every time we multiply the result which we had so far, we multiply it by a and we add the successive coefficient. So first we have fm, then we have fm times a plus fm minus 1, then we multiply it by a and add fm minus 2, and so on and so on. Finally, when we exhausted all the coefficients, when I became 0, we reach the constant term, then R stores the result of the evaluation, so it's f of a, and so we can return R. And as you can see, the number of multiplications here is linear. It's exactly equal m, because at each step we do one multiplication. We have one multiplication here, one here, so m minus 1, m minus 2, and so on, x 2, 1, and 0. So we have exactly m multiplications, m products. So the complexity of the corner scheme is linear, so it's evidently much better than such a naive approach to compute. Our next step is polynomial division, but first we consider only polynomials over a field. We concentrate on polynomials over a field. So if we have two polynomials with coefficient in some field, so in a field means that we have a well-defined division among the coefficients, and of course we assume that G is non-zero polynomial, then there are unique polynomials Q and R such that f is Q times G plus R, and the degree of R is lower than the degree of G. The polynomials Q and R are called the quotient and remainder respectively. Let me now prove this theorem. So denote by the degree of f by m and the degree of g by n. Now we have two cases. If m is strictly smaller than n, when there is actually nothing to do, we can write f as 0 times g plus f, and this is our r in this case, and by the assumption, the condition m less than n means that the degree of r is m is less than n, which is the degree of g. So in this case, if m is less than n, then there is nothing to do. So assume, without loss of generality, assume that m is greater or equal n. Now we can write it is in the following way. We take the leading coefficient, so let c be the leading coefficient of f, so it's f to f with an index m using the notation we used so far, and we take the polynomial r to be f minus the leading coefficient of f over the leading coefficient of g times g times x to the power m minus n. It is clear that the leading coefficients of these two guys cancel, so the degree of f must be strictly greater than the degree of r. We cancelled the leading coefficients. So this way we reduce the degree of r. Now there are two possibilities. If the degree of r is strictly smaller than the degree of g, then we are done. If not, otherwise we can just repeat this step again. So if I denote this step by star, then repeat star. Since each step we reduce the degree of r, the degree of r diminishes with each step, so it's clear that after finitely many steps what we will have is that we have degree f is greater than the degree r, and let's say it that it's the first r. Then we replace r, f and f by r, and we repeat this step star, then we have some degree r2, and so on and so on. So after finitely many steps, the degree of the polynomial r must be finally smaller than the degree of g, and if it's smaller than the degree of g, we are done. Then because we are now in case 1, so the degree of r is less than the degree of g, and this is actually what we want to prove. So this way we proved the existence. This proves the existence of the quotient and remainder of q and r. Now what is left is to prove the uniqueness. So the last thing to do is to prove the uniqueness. So now, uniqueness. So suppose that there are two such pairs. There exists Q1R1 and there exists Q2R2, and that both satisfy the assertion of the proposition, so that the polynomial f is on one side it's Q1 times G plus R1, on the other side it's Q2 times G plus R2. So if we subtract them side by side, what we get is that Q1 minus Q2 times G so is equal R2 minus R1. But now if we look at the right hand side, we have the degree of R2 minus R1 is the degree of the difference of two polynomials. It cannot exceed the degree of any of them. The degree of the difference cannot exceed the maximum of the degrees of R1 and R2. R1 and R2, but we know that this is strictly less than G. On the other hand, the left hand side is divisible by G, so G must divide this difference. If it divides the left hand side, it must divide the right hand side, so G must divide this difference, R2 minus R1, but the degree of R2 minus R1 is strictly less than G, and G divides this difference, so it is possible only in one case, when this difference is 0. So R2 minus R1 must be 0, so these two polynomials must be equal. So what we have is that R2 is equal R1, so we solves one thing, and now when R2 is equal R1, so if we look here, what we get is that Q2 times G plus R2 equals Q1 G plus R1. R1 and R2 are the same, so we can cancel them. So what we get is that Q1 minus Q2 times G equals 0, but G is non-zero, so it follows that Q1 equals Q2. So this actually proves that the polynomials Q and R are unique. This way we proved the proposition. And now the algorithm for dividing the polynomials is again the standard method of dividing the polynomials that you all learned at school. So okay, this is the long division. There are faster methods, but we will not have time to discuss on this course, but this is sufficient for us. So this method works by just comparing just dividing the leading coefficients of the two polynomials. So we start with the quotient to be initialized to 0 and the remainder to be half. It's exactly what I did in the proof a minute ago. And we fix the leading coefficient of G, it will not change, and as long as the degree of a candidate for a remainder is greater than G, so it's not yet a remainder, we just do this reduction step that I did. So we divide the next coefficient of the quotient and we subtract from the remainder what we get here. So let me do one short example. So take for example a polynomial f to be something like 2x cubed minus 4x plus 3, and let's say that g is let's let it be 3x plus 5. So what we do, we divide it by each other. So there are a couple of ways of writing it down. I will use the following notation: 3x plus 5 equals, now we divide the leading coefficients by each other. So we divide these two guys by each other. So we have 2 over 3. This is the first coefficient that we computed, and the corresponding x will be computed next. So actually we know that the exponent is x squared, so I can write it already. However, in the algorithm we don't write it x squared, we just append the coefficient on the right hand side, and the degree of the exponent is just computed automatically. We just compute the coefficient after the coefficient, and the exponent is just computed. We don't need to compute the exponent separately. So we now have 2x cubed and 10 over 3x squared plus 10 over 3x squared, and we subtract them, this cancels, and we have minus 10 over 3x squared minus 4x plus 3. Okay, the candidate for the remainder is the polynomial down here, and it's degree 2, so it's quadratic, so it has a degree greater than g, so we must repeat our step. So now the next coefficient of our polynomial is minus 10 over 9, and of course we can compute the exponents of a variable which is 1, so it's x. However, as I said, in the algorithm we don't do it, it is done automatically. And so now we'll have minus 10 over 3x squared and 50 over 9 minus 50 over 9x, and again we subtract them from each other. So 4 is 36, so now we'll have 14 over 9x plus 3, and again the candidate of the remainder still has the exponent, the degree of our candidate is 1, so it's greater than or equal to the degree of g, so it's not strictly less than the degree of g, so we must repeat the step one more. So it is now plus 14 over 27. So 14 over 27 is 14 over 9x, and now we will 70 plus 70 over 27, and if we subtract them, so here is 3 times 27 is 81. It will be 81 minus 70, so it's 9 over 27, and 9 over 27 is 1/4. So it's 1/4 here. So this is the remainder. This is the remainder, and this is the quotient. Observe one thing that is evident in this example, all the denominators that appear here, maybe I will write this denominator this way, we have the denominators here. The denominators are nothing else but the powers of the leading coefficient of g. So this is the first power, this is 3 to the first power, 3 to the second power, 3 to the third power. So all the denominators which appear in this computation, all the divisions that we need to do are division by the powers of x, is division by the leading coefficient of g. So all the denominators which appear here are the exponents of the leading coefficient of g. So what I said, the only division is the division by the leading coefficient. So since we have a division here, we cannot apply this algorithm in case when the ring of coefficients is not a field. If we cannot divide the coefficients, imagine for example that we work with polynomials over the integers. Then when we divide, we will no longer have an integer, we'll have a rational number. So this previous proposition will not work, and this algorithm will not work over the integers, because the resulting polynomials are not integer polynomials. They don't have a polynomial coefficients. The same is true if we are working with polynomials with polynomial coefficients. So polynomials in variable y, for example, over the ring of polynomials in variables x1 to xn. This is a very important case that we will be working with, but then this algorithm is no longer working here. This algorithm doesn't work because if we divide a polynomial by a polynomial, we don't have a polynomial in general, we have a quotient and a remainder. However, as we observed, the only division that appears in this algorithm is the division by the leading coefficient. So we can make sure that all the divisions are possible, that division of a coefficient are possible, if we pre-multiply the polynomial f by a certain power of this leading coefficient. We first multiply f by a certain power of the leading coefficient, and then it is obvious that all the division will be possible. And such a thing is, such operation is called pseudo division. So if we have a ring of polynomials, but the coefficients are not a field, it's a so-called union. It's an integer ring. So it's a ring where there are no zero divisors, nothing else. We don't need any assumptions. And we have non-zero polynomial g, then there are unique polynomials q and r that satisfy something which is very similar to what we had. Observe that this part here is just the same as before. This is just the division with a remainder. However, here, because the ring of coefficient is not a field, we not necessarily can divide the polynomial, can divide the coefficients. So we have this extra term here. Where is this extra term here, which says that, okay, we pre-multiply this. We first multiply the polynomial f by a power of the leading coefficient of g. Then all the divisions are possible, and we have such a formula. So there exists a polynomial q, which is called a pseudo quotient, and there is a polynomial r, which is called the pseudo remainder, such that such formula holds. And the proof of this is almost the same as the proof of the existence of a quotient and remainder over a field. So the proof that I did a few minutes ago with just a minor modification works here as well. So I will not spend time on reproving it. You can try to do it yourself. And the algorithm for computing this pseudo quotient and pseudo remainder is also almost the same as the algorithm before, because it really doesn't differ so much. Only thing, we pre-multiplied it. So the only differences between the polynomial, between the algorithm we discussed before and this algorithm are in the marketplaces. So the way we compute the next coefficient is that we don't no longer divide. We don't divide it by c. We just multiply it by a power of c, but with a reduced power of c, so that all the terms are actually in the ring of coefficients. And since we change the way we compute the coefficient of the pseudo quotient, we need to, in the same way, adapt the way we compute the pseudo remainder. An obvious advantage of this algorithm is that it can be used in polynomial rings which are not polynomial rings over fields. The important classes of rings for which we use this algorithm are the polynomial rings over the integers, polynomials in one variable over a polynomial ring over the integers, and likewise the polynomial over the polynomial ring in many variables, so multivariate polynomial rings. The last subject in today's lecture is the Euclidean algorithm. Let me shortly recall a definition from a standard course of algebra and or similar subject, that a ring is said to be Euclidean if there is a function defined on this ring with values in the set of non-negative integers, such that this function vanishes only in zero, only at zero. It is multiplicative, it preserves multiplication, and the most important fact most important axiom is that it is well behaved with respect to division with a remainder. Namely, if we have two elements a and b, and q are respectively the quotient and remainder, then this function n on this remainder is strictly less than n on b. This function is usually called a norm, the norm of a Euclidean ring or Euclidean norm. The typical examples of Euclidean domains are the rings of integers itself. Here the norm is just the absolute value, but it's not the only example. Another important example is the ring of polynomials in one variable, so univariate polynomials. Here we see that this remainder of the division has always the degree smaller than the degree of b, but the degree is not multiplicative, so we change it, and the norm is 2 to the degree, because so that way it preserves multiplication. Of course, these are not the all examples. Another classical example is the ring of Gaussian integers, so the ring of all the complex numbers with integer coefficients, numbers of the form x plus yi, where x and y are integers. Here the norm is sum of squares, so it's a square of a standard absolute value. And if we have an Euclidean domain, then in every such an Euclidean domain, so in particular in the ring of integers, in the ring of univariate polynomials, we can apply Euclidean algorithm. The Euclidean algorithm is most easiest form. It's expressed in form of a recursive formula that you see on screen. So if we have two elements, then the greatest common divisor is either A when B is 0, or recursively we can compute these greatest common divisors as the greatest common divisor of A and B is the greatest common divisor of B and a remainder of A modulo B. Let me show you the proof of this formula. The formula has two cases, so the one case is trivial. First assume that B is 0, but then the formula is trivial. Then it's obvious that the GCD of A and 0 is just A, so it's trivial. So the formula is satisfied in this case. So now so we can assume that otherwise B is non-zero. So when B is non-zero, then this is an Euclidean domain, so there exist Q and R such that A is B times Q plus R, and the norm of R is strictly smaller than the norm of B. So what we know? Of course, we know that the GCD, let me denote this GCDs by some additional letter. Maybe let it be just GCD of A and B. So what we have? Of course, the greatest common divisor is a divisor, so it divides both A and B. So what we have is that G divides A and G divides B. But let us look here. On the left hand side we have A and it is divisible by G. On the right hand side we have B plus QR, and so it follows that the G divides the left hand side, so it must divide the right hand side. So G divides the left hand side of the above equality, so it must divide the right hand side. So what we have is that G divides B Q plus R. But now this part is divisible by G already, so from this fact and from this fact we infer that G divides R. But what we have now? We have that G divides B and G divides R. So we will now use this fact and this fact together. So if G divides B and G divides R, it follows that G divides the greatest common divisor of B and R. So we have this fact. So now so we have one inequality, one division here. So the greatest common divisor of A and B divides the greatest common divisor of B and the remainder. So we need only to prove the opposite inequality or opposite division. So what we now take is that G, okay, so the greatest common divisor, what we have, the greatest common divisor of B and R obviously divides B and obviously divides R. Greatest common divisor of B and R divides r. That's trivial. But now let's again look at our equality. So we have this thing, we have this thing, and we have this thing here. So now the greatest common divisor of b and r divides the right hand side. The greatest common so it follows that the greatest common divisor of b and r divides bq plus r, because it divides both b and r. But bq plus r is just a. So the greatest common divisor of b and r divides a. So now we can just look at the last step. I will mark it in green. So we have the greatest common divisor of b and r divides b, and the greatest common divisor of b and r divides a. But from these two facts, we can easily infer that if it divides b and it divides a, so it's a divisor of b and a, but, well, it must divide the greatest common divisor. So every divisor divides the greatest common divisor. So the greatest common divisor of b and r must divide the greatest common divisor of a and b, because it divides both of them. Now, if we look at this thing and this thing here, so we have this thing here and this thing here. So from these two facts, from 1 star and 2 stars, it follows that these two greatest common divisors are equal up to a unit, but the greatest common divisor is defined only up to a unit, up to a multiplication by an invertible element. So the greatest common divisor of a and b equals the greatest common divisor of b and r was the remainder, so it's a mod b. And this is exactly the assertion of our theorem. So this proves the proposition. Of course, we remember that here, as always with greatest common divisor is defined up to a multiplication by a unit, by an invertible element. So for example, the greatest common divisor of let's say 9 and 15 is equally well 3 and minus 3. We usually take 3 as a positive number, but this is possible only in the ring of integers, and in our other rings where there is not well defined notion of positiveness, when there is some imprecision, a little imprecision about the definition of the greatest common divisor. In fact, we can think of greatest common divisor as a set of all these elements. Anyway, we have proved this proposition. This formula for the greatest common divisor can be directly implemented in form of a recursive function. However, if we can change a recursive function into iterative function, if we can solve the recursive formula, it is usually better. Although the recursive functions are usually shorter when implemented, the iterative function does not suffer from the overhead of calling itself over and over. So it's usually preferable to find an iterative formula, if it is possible. And in this case, it's actually very simple, because this formula can be directly translated into an iterative function. So if the greatest common divisor of two elements, so we start with b, and as long as b is non-zero, we just replace a by b and b by the remainder. That's all, and this is exactly the function that we have now. If you have two elements of an Euclidean ring, let's say the ring of integers or the ring of univariate polynomials, then we compute their greatest common divisor in the following way. As long as b is non-zero, we compute the remainder and we replace a by b and b by this remainder. Finally, we break from the loop when b is 0, and in this case a is the greatest common divisor that we are looking for. So again, let me show you a short example how we compute it. For example, take a to be an integer 3256 and b to be a second integer, let's say 2331, and we are looking for the greatest common divisor of a and b using the Euclidean algorithm. So what we do, we compute the remainder. So it's most easy to write it down in form of a table. So we have a, we have b, and we have a remainder. So a is 3256, b is 2331, and now it's obvious that the quotient is 1, the 2000 fits in 3000 just 1, and the remainder is the difference between the two of this, so will be 5, 2, 9. And what we do now, we just shift. We replace a by b and b by r. So now a would be 2, 3, 3, 1. B will be 9, 5, 9, 2, 5. And now we compute the remainder. And now 900 will fit twice into 2000, and the remainder so will be 1850, and if we subtract it, we will see that the remainder is 481. And then again we replace a by b and b by r, so we have 925, 481. So now 481 plus 491 is 960, so it's too much, so the quotient is just 1, and the remainder is the difference between these two, so it will be 4, 4 and 4 again. So again we replace these two guys, so it's 481, 444. It's obvious that the quotient is 1. The remainder is the difference. This difference is easy seen that it's 37. So we do this shift 1 again, 4, 4, 3, 7, and now we just divided. The quotient is 12, and it's exactly 12. So the remainder is 0. So if the remainder is 0, the last shift. Actually, this is not necessary, we do it by hand because we see already the answer. Anyway, this is the answer. This is the answer. This is the last step. So, the greatest common divisor that we were looking for is 37. This shows how the Euclidean algorithm, this classical Euclidean algorithm works. Now, one important fact concerning Euclidean algorithm is called Bezout identity. Namely, if we have still an Euclidean ring, so a ring of integers or a ring of univariate polynomials, then the greatest common divisor can always be expressed as a sort of a linear combination, but this a, b, alpha and beta are not the coefficients, they are elements from the same ring. Anyway, it can be written in the form of such a well, sort of a linear combination of A and B with some elements A and B with some elements alpha and beta from the same ring R. Moreover, for nice rings like Z and ring of polynomials, we can additionally assume that these norms of alpha and beta will be smaller than the norms of B and A. However, in general, I don't know whether it's true or not. So this is the last theorem in this lecture. Let me prove it as well. In order to prove this theorem, I will introduce a sequence of elements defined in the following way: A0 is just A, and A1 is just B. And now I recursively defined all the other elements, so the AI plus 1 will be nothing else but the remainder of, so it's a remainder of AI modulo AI minus 1. So in other words, we can write AI minus 1 is just some QI times AI plus AI plus 1, and of course such QI exists in the ring R. So let's look at the norm. So the norm due to the definition of an Euclidean domain, the norm of a remainder is always lower than the norm of the divisor. So the norm of AI plus 1 is strictly less than the norm of AI for every I. So it follows that the norms form a strictly decreasing sequence. So the norm of A0 is greater or equal norm of A. Okay, here not necessarily, but starting from A1 the norms are strictly decreasing, so the norm of A2 greater or equal norm of A3, and so on and so on and so on. But these are natural numbers. So this must stop. So there is, of course, some index n such that the norm of an equals 0, and this we know because this is equivalent to saying that the Euclidean algorithm stops at a certain place. This is just the way of showing that the Euclidean algorithm stops. But this means that an is 0 by the definition of a norm. So an is 0. So now what we can do, due to the proposition, due to the Euclidean algorithm, we can write that the greatest common divisor of AB, well, A is A0, B is A1, so this is greatest common divisor of A0, A1. But now the Euclidean algorithm says that, okay, if we replace A0 by A1 and A1 by the remainder, the greatest common divisor will not change. So this is the greatest common divisor of A1, A2. And this is the greatest common divisor of A2, A3, again, by the same principle, and so on and so on. Finally, we'll arrive at the greatest common divisor of an minus 2, an minus 1. This will be the greatest common divisor of an minus 1, an. But now we know that an is 0. So there's greatest common divisor of an minus 1, 0, and we know it is just an minus 1. So this is the last element of our sequence, but we can use the fact that we had earlier here. We had this fact, we had this formula, so we can apply it now, and we can express an minus 1 in form of such in this form. So the greatest common divisor of a and b is an minus 1. Now we can express it using the two previous elements, so this will be n minus 3 minus q n minus 2 an minus 2, and now we can do the same thing with an minus 2, so we can write it as an minus 3 minus q n minus 2 times n minus 4 minus q n minus 3 n minus 3. So this is nothing else but this is n minus 3 times something, some element a, plus an minus 4 times some other element b, and so on and so on. Now we'll replace an minus 3 using an minus 4 and a minus 5, and so on and so on. Finally we will go back to a0 and a1. So we'll finally write it as a0 times some alpha plus a1 times some beta for some elements alpha beta, but this is nothing else but a times alpha plus b times beta, and this is exactly what we were after. This is exactly the assertion of our proposition, our theorem. So we actually proved it. We showed that the greatest common divisor is a linear combination of both elements. These two elements which appear here are called the Bezout coefficients. So the standard terminology is that alpha and beta are the Bezout coefficient associated to a and b. And in fact, from what I say, what I proved, just directly implementing this proof of a Bezout identity in form of an algorithm, we obtain the following algorithm, which is called the extended Euclidean algorithm. It is extended Euclidean algorithm just because the standard algorithm is already here. If you look carefully, if we just omitted the steps 3 and 4 inside a loop, what is left is all the other things is just the standard Euclidean algorithm that we just discussed a few minutes ago. So this algorithm just extends the algorithm that we presented before, and it, beside computing the greatest common divisor, it computes the Bezout coefficient. The proof of correctness of this algorithm is just the proof of the Bezout theorem that I just presented, so there is no point in repeating it, but let me show you an example how this algorithm works. I will use the same two integers as before. Nevertheless, now we have a little more columns in our table. So as before, we will have the column A, that column corresponds to the value of A. We will have a column, okay, let me just draw it. We'll have a column B corresponding to the values of B. We had a remainder, but now we will need both quotient and remainder. Quotient and remainder, and we have these auxiliary variables alpha, alpha prime, beta, beta prime. So let it be alpha, alpha prime, beta, and beta prime. Okay, so we start as before. So A is 3, 2, 5, 6, B is 2, 3, 3, 1. But now, according to the algorithm, we need to initialize alpha and alpha prime, beta and beta prime to be respectively 1, 0, 0, 1. Now we compute all the other stuff. Already in the previous example, we computed the reminders, and I computed the quotients by the way too. So here the quotient is 1, the remainder is 9 to 5. And what we do is we replace the respective elements. So B comes here, remainder comes here. Now alpha prime and beta prime replaces each other. So here we have this, and the remainder, all the other stuff is computed. So now we have, so instead of A becomes 2, 3, 3, 1, B becomes 925, alpha becomes 0, beta becomes 1, and we need to compute alpha prime and beta prime according to the formula. As you see, we need to replace alpha prime by alpha minus q times alpha prime, and the same we need to do with beta. One obvious problem with extended Euclidean algorithm, with the Euclidean algorithm and also the extended Euclidean algorithm, that is that it does not work in important rings like ring of polynomials over the integers, of ring of multivariate polynomials, even over a field. These rings are not Euclidean. We don't have division with remainder, so the algorithm does not work there. Nevertheless, the greatest common divisor still exists in this ring. So this ring does have a greatest common divisor. However, we cannot compute it using Euclidean algorithm. But Euclidean algorithm uses reminders, using division with a reminder. Sometime earlier during today's lecture, we learned that we can replace instead of division, we can use pseudo division, and pseudo division is also a good way of computing something which somehow reminds the reminder, namely it's a pseudo reminder. So the question is whether we can apply this idea to compute the greatest common divisor in these rings that we are interested in, and in fact we can. However, this requires some extra work. Most important is that if we have a unique factorization domain, then the ring of polynomials over this unique factorization domain is a unique factorization domain as well. So if there exists a greatest common divisor in the ring R, in the ring of coefficients, then there also exists a greatest common divisor in the ring of polynomials. By a simple induction, this means that the greatest common divisors exist in the ring of polynomials over integers, even in the ring of multivariate polynomials over integers, as well as in the ring of multivariate polynomials over a field. All of these rings are unique factorization domain, and so the greatest common divisor exists there. Only thing that we need to do is to find a way to compute this greatest common divisor, replacing division by pseudo division. Here is how we do it. If we have a polynomial and the coefficient sits in some unique factorization domain, so let's say the coefficients are, for example, integers, then the greatest common divisor of the coefficients is called the content of the polynomial, and it's denoted cont of f. A polynomial is said to be primitive if its content equals 1. Now, the easy observation is that every polynomial can be uniquely decomposed into a product of a content and the primitive polynomial. This may sound okay, some important theorem and the very first sign, but it's actually very trivial. Let me show you how. Let me show you a very simple example. Let's say that f is like 6 plus 9x plus 15x squared minus well, whatever, 12x cubed. Okay, when the content of f is just the greatest common divisor of its coefficients, so 6, 9, 15 minus 12, that's clear that it's 3. So we can write f in a form 3 times, and here is 2 plus 3x plus 5x squared minus 4x cubed. So this is the content, and this guy is the primitive part. This is the primitive part of f. So as you see, this is not a difficult theorem. This is very simple observation. And now the algorithm that computes the greatest common divisor over a unique factorization domain looks like this. It closely resembles the standard Euclidean algorithm. There are only few things that change. First of all, we ensure that the degree of f is when we start, we ensure that the degree of f is greater or equal to the degree of g, is greater than or equal to the degree of g. And what we do on the very beginning, we just extract the greatest common divisor of the content of the two polynomials, and we store it. Through the whole loop, we don't use it, we ignore it, we store it aside. Then we take the primitive parts, starting from point 3. So this part here is nothing else but just the standard Euclidean algorithm with just the single change that we use pseudo reminder instead of a reminder, but everything else is the same. We replace a by b and we replace b by r. However, we have such strange, mystic point 2 here, where we somehow simplify r. I will explain in a moment. But beside that, beside this thing, this part 3 and the loop at 4 is just it looks like just a standard Euclidean algorithm. But finally, when we compute, we stop the loop, we exit the loop, then we return not a, but we return the product, the primitive part of a times this greatest common divisor of the contents of f and g that we stored at the beginning of the algorithm. So the last step that I need to explain is this mystic simplification. In fact, the simplification is can be any function that preserves the primitive part. However, we prefer it to return something that has the same, so it takes a polynomial and it should return a polynomial with the same primitive part, but preferably with simpler coefficients. There are two obvious candidates for this function. First of all, we can omit this step at all. altogether. We omit this step, we just take the identity, so there is no simplification at all. We take identity, so we do not simplify at all. This, as we will see in a moment, I will show an example. This produces a very large intermediate coefficients. Even if we start with polynomials with having small coefficients, the resulting coefficients that will appear during the algorithm can be enormously big. In fact, we suffer from explosive growth of immediate coefficients. This is one of the very bad phenomena that appear in symbolic computation. Here we see it for the first time. So the other extremum is to replace the polynomial but its primitive part. This may sound very smart at the first sign, because okay, we want to preserve a primitive part, so we let us just compute the primitive part. Then the coefficients will be so small as they can only be. Okay, that's true, the coefficient will be very small. However, the cost of it is that we will have to compute a very large number of greatest common divisor. You can imagine that, for example, we compute the greatest common divisor of polynomials in three variables, x, y, and z. So we treat them as polynomials in z over the ring of polynomials in x and y. And if we use this second idea of computing the primitive part at every step, so at every step when we need to find the primitive part of polynomial with respect to z, so we must compute the greatest common divisor of the coefficients, but coefficients are polynomial in x and y. So we compute the greatest common divisor of a number of polynomials in two variables. Now, in order to compute it, using again step 2, strategy 2, we will have to compute for each of them, compute a greatest common divisor of their coefficients. So, as you see, this is a cascading, this is kind of recursive cascading formula that at each level we have more and more greatest common divisor to compute. So all in all, we will end up with such an enormous number of greatest common divisor that we need to compute that the resulting coefficient will be as small as possible. But the number of computations, the complexity of the computation will be killing. So we may wonder if there is something in between. Yes, there is something in between. We will not have time to discuss it during this course. This course, as I said on the very beginning, consists of only 15 hours of lectures, so we will not have time to discuss it. But such an algorithm is called the subresultant polynomial sequence, and it's due to Collins. I strongly encourage you to look into the lecture notes to this lecture that to this course, the lecture notes of this course that I provided. The link is provided below, and you can see how this algorithm works with subresultant. It is really the optimal one. However, we don't have time to discuss it. But before I finish this today's lecture, let me show you examples of using these two first strategies. So if we do not simplify, so we will take the same two polynomials, one of degree 8, one of degree 6, that you see here. So this polynomial and this polynomial, and we compute the greatest common divisors both times of both of them. So we have here and here. As you can see, if we have no simplification, then the coefficients can really explode. What we have here is that the coefficient becomes enormous. The polynomials themselves have all the coefficient not greater than 21. The 21 is the biggest coefficient. It's the only coefficient with 2 digits. And once we compute this stuff, at the last step we have a coefficient of, well, I don't know, but a lot of digits. We will not spend time on computing it. On the other hand, of course, now the last step of this algorithm is to take the primitive part of it. If we take a primitive part of it, then the primitive part of a single coefficient of a constant polynomial is 1. So we'll get 1. And here we get 1 immediately because we take the primitive parts. So as you see, all the time we have very small coefficients, as small as possible. At most we have 4 digits. However, this costs us a lot because we have to compute lots of greatest common divisor of the coefficient in between. Now, in order to conclude this lecture, let me mention that if we can compute the greatest common divisor by the well-known formula for the least common multiple, we can compute the least common multiple as well. That's all for today. Thank you for your attention. On today's lecture you learned some very fundamental, very basic building blocks for algorithms that we will be developing throughout this semester. On the next lecture in 2 weeks you will learn some more advanced stuff. In particular, you will learn a much faster, a superior algorithm for multiplying polynomials, which is superior to the 2 algorithms that we learned today. Thank you.